Nuclear Energy, A Brief History. Rousseau Jean-Claude, published in French, December 8th, translation, October 8th. Before considering the role of nuclear power in the future electricity mix, it is important to know the origins of the industry, from the chance discovery of one uranium rays. At the beginning of the TH century to the operation of a worldwide fleet of reactors, the history is short but very rich. At the end of the 19th century, 1800s, a majority of scientists thought that there was not much left to discover in the field of physics. The atom did not exist. Some academics even said so. Scientific discoveries. The history of nuclear energy began by chance on March. For some time, Henri Becquerel, at the suggestion of Henri Poincaré, had been studying the fluorescence of certain materials. He placed a photographic plate, wrapped in black paper, next to a salt of uranium sulfate that was supposed to emit X-rays when exposed to sunlight. In short, the uranium sulfate exposed to the sun becomes charged with light energy. It is then able to give it back in the form of electromagnetic waves in the X-ray range. On that day, March, Becquerel discovered that the blackening of the photographic plate occurred even when the salt was not exposed to sunlight. It therefore does not fluoresce. Uranium and its compounds emit specific rays by themselves. We will call them uranium rays for the time being. From then, each year brought its share of discoveries. Ernest Rutherford identifies 3 types of radiation that he called alpha, beta, and gamma. Marie Curie, born Maria Sklodowska, discovers another element with the same properties of emitting these rays. It is radium. She evaluates its atomic mass approximately and invents the word radioactivity. With her husband Pierre Curie and Henri Becquerel, she received 2 Nobel Prizes in 1903 for having discovered natural radioactivity, and in 1911 for having determined the atomic mass of radium figure 1. Niels Bohr applied his quantum theory to the hydrogen atom. Fig, Pierre, and Marie Curie. Source, FRM, Wikipedia.org. From 1913 to 1928, the Copenhagen School, led by Niels Bohr, laid the foundations of quantum mechanics. Paul Dirac, Wolfgang Pauli, Erwin Schrödinger, and Werner Heisenberg were instrumental in establishing this theory, understanding the atom, and explaining radioactivity. James Chadwick established the existence of the neutron. The nucleus of atoms took on its current, form as an assembly of protons and neutrons around which electrons gravitate. Starting the neutron, because of its electrical neutrality, became the projectile of choice for bombing all types of elements. One clever scientist, Enrico Fermi, in Rome, conducted a new kind of experiment. He bombarded the last known natural element of the Mendeleev table, and therefore the heaviest element, with neutrons. By bombarding uranium, he hoped to find new elements and transuranics. But he came up with a perfectly incomprehensible result. It was not until that he began to unravel the truth and understand these experiments of bombarding uranium with neutrons. That summer, Irene Curie and Frédéric Joliot discovered, among the products formed by the bombarded uranium, a particle that seemed to have all the chemical properties of lanthanum. But what would it be doing there? They were very close to the truth, but did not dare to publish it. In December of the same year, Otto Hahn discovered barium in bombed uranium. He then dared to suggest that the atom's nucleus had broken up. He had discovered fission, which generated an extraordinary amount of energy. The following year, Frédéric Joliot, Hans Halban, and Lou Kowarski at the Collège de France demonstrated that, in addition to fission products and a large amount of energy, that fission also produced 2 or 3 high-energy neutrons. They imagined the possibility of a chain reaction. The group took out 3 patents on behalf of the Centre National de la Recherche Scientifique, CNRS. These patents, which are very complete, can still be consulted at the Commissariat à l'Énergie Atomique, CEA. They provide all the information needed to build a nuclear reactor. Fig, French atomists. Source, L'Histoire, military applications. These patents were not respected by the United States. With the outbreak of the Second World War, the U.S. became the masters of nuclear energy research and its use. On August, Albert Einstein wrote to President Roosevelt to draw his attention to the new source of energy, represented by uranium, and to the possibility of building a bomb. He did this at the request of Leo Szilard and Eugene Wigner, physicists of Hungarian origin who feared that Nazi Germany would acquire an atomic bomb. From October to June, the facilities needed to build an atomic weapon were quickly put in place. The Manhattan Project, led by General Leslie Richard Groves and physicist Robert Oppenheimer. The United States provided the resources. 3 parallel isotope separation projects were launched in the summer of. The gaseous diffusion method, finally judged to be the most promising, was industrially developed at the Oak Ridge Center in Tennessee, where construction of the plant began in late. At the same time, on December 2, 1942, Enrico Fermi diverged the first graphite-moderated natural uranium atomic pile. This took place under the stands of the Chicago Stadium, from which the famous photo has been preserved, bringing together, near the graphite pile, the cream of American physics at the time. Enrico Fermi, Eugen Wigner, Arthur Compton, and a few others. At the top of the pile is a man is ready to slice with an axe the rope that will free the safety bars, just in case. All these physicists, in fact, are totally unaware of the speed at which the reaction will develop. They know that the average lifetime of a generation of neutrons is of the order of 1/10 of a millisecond. With only these so-called fast neutrons, the reaction can only get out of control and lead to a dangerous flash. Fortunately, nature has done things well. In each generation of neutrons, so-called delayed neutrons allowed the reaction to be controlled. Enrico Fermi more or less knew this, but he was not sure of himself and took precautions. Figure 3, Enrico Fermi, 1901 to 1954. Source, Biography Online. A new step was taken in March 1943 with the arrival at Los Alamos of Robert Oppenheimer and a group of physicists charged with carrying out research on the criticality of uranium and plutonium, the latter being supplied by the enormous graphite batteries built in record time at Hanford. The results of this work were the development of a first bomb, tested at Alamogordo Trinity Test, and then of 2 other bombs. The second bomb, Little Boy, was fueled by enriched uranium. The third, Fat Man, was fueled by plutonium. Both were dropped over Japan. Although not glorious, this act contributed to stopping the war, and probably to preventing a third world conflict. Electricity production. In December, the Americans produced the first nuclear energy at the Idaho Falls site with the EBR reactor, which enabled them to light the small town of Arco in the state of Idaho. Over the next 4 years, development efforts intensified in the United States, the Soviet Union, the United Kingdom, and France to move towards civil nuclear power. The first prototype power reactor was commissioned in Shippingport, near Pittsburgh, Pennsylvania, It is a MWE pressurized water reactor, PWR. An atom is made up of a nucleus of protons and neutrons, around which electrons gravitate. The binding energy of the elementary particles inside the nucleus is a few million times higher than the energy that binds the electron to its nucleus. This observation allows us to understand why we can extract a few million times more energy from the fission of an atomic nucleus than from the simple chemical reaction of this atom during combustion. In other words, 1 gram of uranium can produce as much energy as several tons of carbon products, coal, oil, or wood. How do we obtain this gram of uranium? Natural uranium is essentially made up of U, which is non-fissile and therefore does not enter the nuclear fission reaction, and only. Of fissile U, only the latter is capable of providing fission reactions. To carry out fission, slow neutrons, known as thermal neutrons to KMSEC, are needed. whereas the neutrons generated by the fission of the previous generation are fast, km sec. It is therefore necessary to slow them down. Light materials such as hydrogen, deuterium, and isotope of hydrogen or graphite are good moderators. The neutrons, by successive shocks on the atomic nuclei of these materials, will thus slow down and be likely to create new fissions of the U nuclei. Graphite, which does not capture neutrons, has the advantage of being cheap and allowing the use of natural uranium. Deuterium, in the form of heavy water, also has a very low probability of neutron capture, while allowing the use of natural uranium. The problem is that heavy water has a very high cost. It is produced by fractional distillation of ordinary water, which contains a very small proportion of heavy water. Hydrogen in the form of ordinary water slows down neutrons very well, but unfortunately also captures them. It is therefore necessary to enrich the uranium to the level of U to maintain the fission reaction. When France, considered using nuclear energy, it had no other choice than graphite as a moderator because it allowed the use of natural uranium. It is the natural uranium graphite gas line, cooled with pressurized carbon dioxide, in parallel with the test of the heavy water gas line with the Brenneless prototype in Brittany. Great Britain also chose graphite gas with its Magnox line, while Canada opted for heavy water in the framework of its CANDO program. The United States, for its part, took advantage of the existence of enrichment plants to develop light water lines, PWR, and boiler power reactor, BWR, which allowed for more compact reactors that could be scaled up to very high power levels. However, since Enrico Fermi, all physicists know that the future lies with fast neutron reactors, in which neutron slowing is avoided. These reactors are capable of converting of U fertile into plutonium fissile. The Pu, previously considered as a troublesome waste product, becomes a useful fuel. The amount of energy that can be extracted from natural uranium is thus multiplied by a factor of or more. Under these conditions, the specter of a nuclear fuel shortage disappears. 4. The French nuclear program. For more information about the impressive French nuclear program can be found here, www.encyclopediaenergy.org/on/nuclear energy brief history/ nuclear programs around the world. As of, nuclear reactors are in operation worldwide, with a total capacity of GWE spread over countries on 4 continents. The countries with the largest nuclear power capacity are, in order, the United States, France, Japan, and Russia. From 2, the United States built PWR and BWR reactors, representing an installed capacity of just over GWE, the largest in the world. Even though it accounts for only 20% of the country's total electrical capacity. On March, the 3 Miles Island accident shattered the dream of considerably increasing this share. Although this accident had no radiological consequences on the environment, the government decided on a moratorium on the construction of new reactors. A recovery began, but was halted by the fall in natural gas prices caused by the development of shale gas. From 2, Électricité de France, EDF, started up 6 UNG reactors. France was second only to the United States in terms of the number of reactors and installed capacity. But it was well ahead in terms of the proportion of nuclear power in electricity production. Poor in fossil energy sources, Japan relied early on the development of nuclear power to meet its rapidly growing electricity needs. At the beginning of, BWR and PWR reactors were providing more than wave power. The Fukushima disaster, caused by an exceptionally large tsunami on March of this year, halted the use of this energy source, whose future is now uncertain. As evidenced by its low contribution to electricity production Russia had reactors with a total capacity of GGW. These are mostly VVERs, similar to Western PWRs, as well as RBMKs, enriched uranium, graphite moderated, and light water cooled reactors. Under certain conditions, the latter are subject to operating instabilities that led to the Chernobyl accident in 1986. Western countries had studied this type of reactor in the S, but, knowing the risk of instability, had never considered building it. Country number of reactors, nuclear capacity, percent of energy derived from nuclear power. France, Slovakia, Belgium, Ukraine, Hungary, Sweden, Switzerland, Czech Republic, South Korea. Japan, Finland, Germany, United States, Spain, Taiwan, Russia, United Kingdom, Canada, India, China, world. Source, CE, Eleknuk, ed. The rest of the world's nuclear power belongs to Germany, whose reactors will soon cease to operate since, under pressure from the Greens Group, the country has decided to abandon all activity in this sector. From the United Kingdom developed graphite gas reactors as early as. From these, it obtained an output of around GWE. But production was halted by the discovery of oil and gas in the North Sea until the recent resumption of activity, which has resulted in several PWR projects and possibly an EPR. Canada, various other European countries, and emerging Asian countries, South Korea, China, Taiwan, India, do not seem ready to give up nuclear energy, given their great need for electricity and the scarcity of other energy sources. In 2017, the World Nuclear Association, WNA, recorded an installed capacity of 392 GWE from 352 active reactors, many of which are no longer in operation, particularly in Japan, representing a production of 2,506 TW. Its targets are GWE, or of the global electricity mix. Further reading, Commissariat à l'énergie atomique, years of nuclear power. Regarde sur l'actualité. Le nucléaire français, quel avenir la documentation française? Bonim Bernard 2012. Le nucléaire expliqué par des physiciens. Preface by Etienne Klein, EDP Sciences. Some edits made by M. Iyer to adjust readability level. March